Can't seem to get the recording done. All right, class, let's go for it. 7.3, maybe we'll make it to 7.5 today. We're going to try here. This is going to be a little bit of a push. I would rather do it in class than outside of class here. So real quick here, 7.1 was just an intro to hypothesis testing. We good? We grab a little sample, we do some testing on it, and then we infer something that's going to happen to the population. We figured out we could either do it by p-values or we could do it by critical areas, right? We figured out the area that's needed for a 95% confidence or 95% alpha level, and then or 99% or 90, depending on how strict you want it. At that point, we go for it. And then 7.2, let's jam with this one here. 7.2 was that we knew the mean, and we're going for the mean. We're testing for the mean. Is this average or not? Is it likely to be the average or not likely to be average? And we had one thing. We knew that the standard deviation of the population. And that's usually given if you've done these tests before. There's some data that has given you, like, yeah, we know the standard deviation of the weight of Americans, let's say, right? Enough tests have been done on that where you know the standard deviation. Okay, so real quick here today. So last time was testing for the mean if we knew the standard deviation. Right here, we're going to test for the mean again, but now what happens if we don't know the spread of the data? So we got to do it a little bit different. And I think we have something called the t-test for it. You guys remember the t-test? We did it in chapter 6. It's just when you don't know the population standard deviation. That's what the t-test is for. All right, then we're going to do hypothesis testing on proportions, pretty much percentages, if you think about it. And then instead of the mean, we're going to do it on the variance and the standard deviation itself. So let's jam with it. Let's go. So I'm going to go with let's go here. The t-values. That's what we're going to go to directly here. So let's go to here. Let me go, don't need to write this down, but let's just kind of go through the list here because we're going to follow it enough. So on these ones, we are going to have to figure out the alpha level we need, and that's usually given. And because we're going to do the t-test or the t-table, we're going to have to do the n-1 for degrees of freedom. Again, don't need to write it down because we're going to practice enough of times with this that we're going to know this. And then what we do is figure out if it's a left tail test, a right tail test, or is it a two tail test? There's that difference. So we were doing that last time as well, right? Remember, I would have separate the percentages to make sure it fits correctly in where it needs to be. So a little graphic of it. Here's a left tail test for a t-distribution, a right tail test, and then we might have to do both. So we would do is if it's a both test, we cut the alpha level in half to compensate for that. But we're looking for the t-naught in each case here. Okay, let's practice just a little bit here with this stuff. Practice the left tail test. Can you find the critical value t-naught for a left tail test given that alpha is 0.05 and the n value is 21? So we have 21 participants. There's 21 people in the class. And so give me the t value that will sort of be that by there. So grab your textbooks if you have them. And we will jam to table 5. Table 5 is this right here. Boom. We're gonna have to pull the t value off of this table here. And that's cool. Your table actually does already split it for you already. Notice this has a one tail alpha and this has two tail alpha. And so it kind of already gives you the split there. Okay, so let's go for it here. On the table itself, let's see if this makes sense. We have degrees of freedom. So there's 21 participants, 21 people in the class. 21 minus 1 is 20. So along the chart going down, we're going to go down to 20. Using table 5, and the alpha is a 0.05, and it's a one-tail test column. And you guys tell me what you guys get. don't know. Okay, you're gonna be shy. All right, let's go with it here. So the t-value, we get it from the table, is a 1.725. We good? Hopefully everybody found that 1.725. Quick raise your hands if you didn't. Now, the only little thing that we got to think about is this. Because it's a left-tailed test, we're going to use a negative of that value. Notice all the t-values in table 5 are all positive. So at this point, you got to just know which side you want to be on. Good. So there it is. If we were to draw it out, alpha level is 0.05. We've got a t-value of negative 1.725. Okay, talk to me. Just making sure. T-values do have to go off of table. All right, raise your quick hand, raise your hand if you got it. If you have a textbook and you got it. Okay. Yeah, for these, I'm gonna have to print you out table 4 and 5 for the exam for sure. As we do these. Okay, another one here, real quick here, try it again. It is, I need an alpha level 0.01, so 99% level, and n is equal to 17, all yours. Give you guys a few seconds, try it yourself. I'm going to check on something real quickly here. I want to see if yeah. Oh, okay. All right, let us continue here. So let's see, degrees of freedom would be 1 minus 17. 1 take away from 17 makes 16. Use table 5, alpha level 0.01 in the one tail column. And you get an answer of 2.583. Take a look at it. Take a look at the column. Make sure you guys get it. The graphic for it looks like this. So alpha 0.09. So 99th percentile, technically. That's what we're looking at. Looking at there. Okay. One more type here. And let's go with this one here. It's a two-tail test now. So for a two-tail test, alpha is given at 90%, so 90th percentile. A lot more loose as far as the answer. N is equal to 26. Give you guys a few seconds, go for it. All right, so we'll go with 25 is what we're looking at. Alpha is a two-tail test this time. And plug it in to 0.01 in the two-tail column. It's going to be both a negative and a positive value this time. And how about a negative 1.708 and a positive 1.708? Are we good? Okay. Thumbs up if we're good. Thumbs up if we're not good. Okay. There's the graphic right there. So it's technically, if you see it, a two-tail test at 90% is really a one-tail test at 95%, really. Kind of if you think about it that way, right? Because you split the remaining piece into two pieces. Okay, there it is. Do it by table, let's jam. So now let's look at the formulas. Formulas, here we go. Since we do not know the standard deviation, all that changes from a z-score to a t-score. So what we do is we take the sample mean, subtract from the mean or the mu value, and instead of putting standard deviation right away, we're going to put the standard deviation of the sample divided by the square root of n. We've done this before. That was during chapter 6 when we did confidence intervals. All right, tell me you're done, and we'll just jam with some examples here. 3. All right. And again, don't have to write down all of that, right? You just put t-test for the mean and then put in the formula itself. All right. And again, the process, I think the process is exactly the same that we've done before. We good? 2.7.2 is very, very similar. It's the same process, just using the t table. So don't think it's something super duper new. So formula, have it written down, and we're just going to plug in the formula as we go. Okay. Tell me if I'm going too fast, otherwise we'll go. So we go here. So don't need to write down everything. We'll just set up the problem though. So used car dealer says that the average price of used cars sold in the last 12 months is at least $21,000. You suspect the claim is incorrect and find that a random sample of 14 used cars sold in the last 12 months has a mean price of $19,189. Standard deviation is almost $3,000. So the question is this: is there enough evidence to reject the dealer's claim at the alpha level 0.01? Assume the population knowledge. So let's pull the numbers that we need out of it here. Is at least 21,000. So we're looking at greater than or equal to 21,000, right? So alpha level is given. That's no need there. So I guess we've got to figure out what is HA and HO. Really, as soon as we figure that one out, we're good. So remember, HO includes the equal sign inside it, right? So because we want to know is at least 21,000, it's going to be mu is greater than or equal to 21,000. And then that's the claim by the dealer. That means the alternative hypothesis is mu is less than 21,000. Okay, also give me your degrees of freedom. What's the degrees of freedom here? How many cars did they look at? If anybody remembers. Yeah, they looked at 14 cars, so that means degrees of freedom would be one less, is just 13. So the claim is made. That's cool. We identified the null hypothesis, alternative hypothesis. Degrees of freedom is now 13. We have an alpha level 0.05. That's perfect. Let's go get our t value. So what is our t value for this problem? Or t naught, if we like. So this is going to be our border for the rejection region. All right, so I'm going to look at my chart again here. So 13 is what I'm looking at. I'm looking for a left tail test. I'll go with that here at negative 1.771. Are we good there? Hopefully found that one. All right, and then this one, got to plug in the values here. So here's what the average was, average claimed, standard deviation of our sample divided by the square root of 14. And we get ourselves a negative 2.297. So question is, what is happening here? So question is, are we in the rejection region or not in the rejection region? Cool. Okay, so let's see the graphic of it. And if you want to make the graphic of it, this is what it looks like. So we're comparing T naught to the T that we found. And so we have the border of our rejection region is a negative 1.771. The T value that we got from our piece there is a negative 2.297. So the question is, do we reject the null hypothesis? Absolutely, right? So we say this right here, there is enough evidence at the 5% level of significance to reject the claim. The mean price of used sold cars last year is at least 21,000. Okay, you guys talk to me here. We'll do two more here in just a bit. You guys just tell me if that makes sense. And notice, I really want you guys to notice the process is still the same, right? You figure out degrees of freedom, you figure out the T value that you need, and then you calculate your T value and see if it lies in the rejection region or not. The setup is probably more thoughtfulness here than just crunching the numbers and done. Okay, any questions on this one? You guys talk to me. Makes sense? Flying over the head. What do you guys say? Sort of. Okay, maybe do a couple more, see if that makes sense. See if it sinks in. Let's do this one here. So an industrial company claims that the level of pH of water nearby river 6.8. You randomly select 39 water samples and measure the pH. The mean sample is 6.7. Standard deviation is 0.35. So is there enough evidence to reject the company's claim at alpha is equal to 0.05? So this one's going to be more like an equal to, right? The company is claiming that the river is actually equal to 6.8. So to me, that looks like a two-tailed test to me. Does that make sense to you guys? Okay, so H naught is the one that holds the equal. So let's put stuff together. And again, H naught, HA is the first listing. Degrees of freedom would be the next listing. Calculate the T value we need for the border of the critical region, and then calculate our T value from our sample. That's it. So H naught and HA, what are the claims here? So the claim is that the average or the pH level is 6.8. That's the claim. That means the alternative hypothesis would be that it's not 6.8. As soon as you see that, you know you're in a two-tailed test. Okay, so you guys talk to me here. Let's see. We have 39 samples. Degrees of freedom would be 38, sorry. Can't give you all the information here. So it's a two-tailed test. That is true. Level of significance is alpha 0.05. Degrees of freedom is 38. And we use the tables 5 to get those values for us. So can you guys graph this for me? That'd be a good one to sort of try to do. Graph the pieces, tell me the border of your rejection regions, and then put a little dot where we find a negative 1.784. All right, see a few people still writing things down here. I'm going to pause just a little bit here. Let me just walk around, see how you guys, where you guys at, understanding, and then can you graph it for me? That's what I'm looking for. I'm looking for the graph that makes sense for the numbers here. All right, here it goes. So if I graph this, you go up and down. The t values that you looked up on your chart go right there. They're the borders of your rejection region. And then the t value that you calculate, you're just going to put a dot, and the dot goes where it is. So notice, oh man, we didn't get to the rejection region yet. Therefore, we failed to reject the null hypothesis. And so we fail. So we say there's not enough evidence at the 5% level to reject the claim. Okay, we're good there. Hopefully that makes sense, because we're going to be doing the same exact concept over again. Cool. Anybody else need more time? Go once, go twice. All right, 7.4, hypothesis testing for proportions. Again, same exact process, slightly different formula. Other than that, everything works exactly the same. And chapter 6 and 7, you should see the connections between the two, right? Because we were doing confidence intervals then, but we did each one. We did it for the mean, knowing the standard deviation, mean without the standard deviation. We did it for proportions, and we did it for the standard deviation and variance. So the formulas that you're going to see are going to look very, very similar. All right, so let's go with it here. So on to proportions now. So formula, there it is, the z-test for population proportions. Remember how we had to compare it to 5? We're trying to figure out if we can use a normal distribution, the number of people in the sample or study times your success has to be greater than or equal to 5, and the number of people times your failure rate has to be greater than or equal to 5. So that's something we have to test for. And then here's our formula for our statistics, our z value here. We have to figure out the sample proportion. Once we do that, we take it away from the average of the population proportion divided by the square root of our proportion, or in this case, it's going to be the square root of P times Q, success times fail, divided by N. And really all these is just the same process here. All right, tell me when you guys are done writing it down, or I'll look around to see, and then we'll go on. Okay, let's go for it here. An example here. Here's what we got. So researcher claims that less than 45% of US adults use passwords that are less secured because complicated ones are too hard to remember. Okay. Random sample of 100 adults, 41 say they use passwords that are less secure because complicated ones are too hard to remember. That's the reason for it. So alpha is equal to 0.01. Is there enough evidence to support the researcher's claim? Less than 45. So really he's saying that most people are using hard to remember passwords nowadays. right? Because less than 45 use easy ones, right? That means the majority is using more difficult ones. And for, I've like, whenever I did banking last like 2 years or so, I know you log in and it says, in order to beef up security, right? You guys have had those? We would like for you to do a password that includes capital letter, lowercase letter, right? At least 8 characters, special, what is it? A special character, right? And then a number. So I think companies, as they do that, I think we get sort of modeled into that, I think. So anyways, the researcher claim is this. Okay, you guys talk to me here. First things first is, what is your H naught and HA? That's kind of, even write it down right now. What is H naught? Put it down there, write HA. H naught has to include the equal sign inside it, that's all. So think about which one has the equal sign inside it. So H naught, HA, and then after you do that, then tell me what the claim is. Which one's the claim? So because this is a proportion, we'll no longer do mu, right? No more mu because this is a proportion. So we're gonna have to do P. So the researcher claims that less than 45%. So I'm gonna write this one down first. Are you guys okay here? P is less than 45 or 0.45, I should say. So 0.45. That means the flip side would be P is greater than or equal to 0.45. And which one is the claim? Top or bottom? Cool. Show of hands. Let me say top is the claim by the researcher. Bottom, how about bottom is the claim by the researcher? Oof. So the claim that, there it is. So this guy has to be the claim. Okay, we're good there. All right, read off the value itself. The claim is that less than 45%. That's cool. So now the question is this: assuming this is true, assuming that's true, this. We want to do a nice specific graph though yet here, right? So that P is going to be greater than or equal to 45. That's a one-tailed test, is that right? A left or right tail test. So if that's true, the only rejection region here is actually on the left-hand side. Is that right? It's kind of like that, right? If everything is either greater than 45 or above, that means the rejection region has to be towards the left. Okay, think I'm good here. So let's try this. First things first, before we even begin, can you guys tell me real quickly here? I just need to make sure this is true. Is NP greater than or equal to 5 and Q greater than or equal to 5? So how many samples did we do? 100. 100 times the p-value. P-value is 0.45. Is that greater than or equal to 5? Yeah, that's 45. That's huge. 45 is, yes, maybe bigger than 5. Okay, if 45 is the p-value, the q-value has to be 55. 50.55 times 100 gets you 55 greater than or equal to 5. Cool. Okay, are we good there? Can we use this? Can we model this proportion? Using technically the binomial theorem, or sorry, the normal distribution. Yes, absolutely. Okay. You guys talk to me here. Can you guys figure out alpha is 0.01. It's a one-tailed test. So I'm looking at 1% being over here, or 0.0100 right here. What is my z-score of 0.0100? So we're looking for percent, we're looking for proportions, right? And looking for a z-score. So going backwards. The closest one I get, so if you look at your z table, table 4, you got a 0.0099, and then you got a 0.0102. So at this point, this guy's closer, right? It's only 1/10,000th off. We're good. This is 2/10,000ths off, so we're going to reject. So this one's going to, if you point across, this is a negative 3.2. If you go up, it's 0.03. So my rejection region is a z-score of negative 2.33. That's what I'm looking for. Okay. Oh, can't show you this one yet here. So there it is. Oh yeah, rejection region. Any z-score of less than negative 2.33, I'll fall into the rejection region. Okay, your job. Can you use the formula and find to me our calculated z-score? When you find it, tell me. All right, let me actually go back to what, there it is. Here's your formula if you want to take a look at it. So calculate your z-score here. Right, I'm going to try. So look up if you've tried it once, see if you guys can get that. And then let me do this here. Let me walk around to see if you guys don't get that. What I would suggest is to calculate the top first and then just divide it by everything on the bottom. So let's do that here. I'm going to try to mine as well. So 0.41 minus 0.45. I got that. I divide that by the square root of 0.45 times 0.55 divided by 100. Now, the only thing is I'm not putting extra parentheses on here because if you just have one thing in your denominator, you're absolutely fine. It's just going to keep it there. So negative 0.80 looks like if we're going to do 2 decimal places to our z-score, negative 8.0, negative 0.80. Okay. Let's do this. Raise your hand if you don't have that. Let me come by and help you with it. If you do, perfect. Okay, so then, again, can you draw for me the normal curve, with a standard normal distribution. Put your borders for your z-scores, and then tell me the calculated z-score. And does it fall in the rejection region, or doesn't it not fall in the rejection region? All right, here it is. Here's what I got here. So if you graph it, remember, you're only going to graph one side, right? So your normal distribution, middle 0, and your z-score negative 2.33 is your border, and your calculated one is negative 0.8. That's inside here. It's not in the rejection region, so we failed to reject the null hypothesis. Okay, we're good there. So failed to reject it. And that actually was our claim. Our claim was the alternative hypothesis, huh? Yeah, the alternative hypothesis here. Okay, cool. So at this point, there's not enough evidence at the 1% level to support the claim that less than 45% of US adults use passwords that are less secure because of that reason. Okay, that's one. So notice all the things were given to you, right? We just calculated Z. One time, sometimes some things are not given to us. So sometimes the p-value is not given. So let's do this one here. So yeah, I just got 1, 2. Problems are long, but they're still the same process. Long. So let's go for it. Sample proportions. Here it is. Sometimes when you're given the information, the sample proportion is not given. They'll give you a whole bunch of numbers, but then the p-value is never given. So we can still get the p-value ourselves. We just have to figure out the number of people that were successful in what we're trying to do versus the number of people total. All right, just takes us just one more extra step just to calculate the p-value. That's about it. The rest of it is exactly the same. So let's try this here. All right, I don't need to write everything down here, just the p hat equals to x over n. That's kind of the important part there. So let's try another one here. We're just going to calculate this little piece right here. That's all. Everything else remains the same. So let's jam. Here it is. Researcher claims that 51% of US adults believe. Better read up on that. Incorrectly, that antibiotics are effective against viruses. Are antibiotics effective only against bacteria? Is that what I'm trying to say? Okay, so p-value is not stated. We don't have a 0.45 anymore here. So in a random sample of 2,202 adults, 1,161 of them say antibiotics are effective against viruses. So at the alpha of 90%, is there enough evidence to support the researcher's claim? So let's go back to the researcher. Claims that 51%. Ooh, that sounds like a two-tailed test to me, doesn't it? So that means exactly 51%. It doesn't say more than 51%, less than, it says that 51% of US adults believe, a little bit over half. So is it enough evidence to support the claim? All yours here. So first things first, I guess, so we don't jump the gun here this time. We can do it, yeah. H naught, HA. Let's set that up like we did last time here. Oh. It's all yours there. I use P as your condition. Oh, sorry, Z, sorry. Yeah, sorry, P. Okay. So the claim is that 51% of US adults believe antibiotics are effective against viruses. I assume antibiotics are effective only against bacteria, I guess. Right? That's kind of what I'm thinking. That's what it's trying to say. Okay, so I'm thinking this is right here. Is that right? True there. So that means this is not. So to me, that speaks of a two-tailed test right away. And we can multiply them to test. So let's test NP if it's greater than 5 and test NQ greater than 5, greater than equal to 5. But with 2,202 adults, that's going to be pretty, you know, that's going to be bigger than 5. We're good. That's like in the thousands. It fulfills it. This one again, 2,202 adults. 49%. Yeah, definitely that's going to make it. Okay. Oh, yeah, I forgot. Which one's the claim? H naught or H alternative? H sub A. H top, yeah. That in fact that it is. He claims that yes, 51%. So the claim is H naught. Okay, cool. I got that already. So now let's figure out the z-value that will work for us. So at the 90% level on a two-tailed test. So that means if I'm thinking like this, I'm thinking here and here. So that means 5% has to go here. And 5% has to go here to split off the two different pieces here, right? So what is the z-value that I'm looking for? Anybody with that? So it'd be a at the 5%. Z-score or 0.0500 for your all right, anybody got that one yet? What's the Z-score? That would help us out here. Two-tailed test, it's at 90%, so that means each of the sites have to have a 5%. So you can, because of it's a two-tailed test, it does help you out a little bit. You're on table 4 on the negative Z-value table in your book. Notice that over here, it has the confidence values or critical values over here on a two-tail, which kind of helps you out right here. So at this point, at a 0.90 with 5% on each side, it's a 1.645. Are we good? Kind of gives you the two-tail test right here, which is kind of nice. Okay, everybody found those. So I got myself a negative 1.645 and a positive 1.645. That's what I'm looking for. So here it is. My critical values are negative 1.645, positive 1.645. Now let's go on. Let's calculate our Z value. So if you want to, you can draw this out now. Draw this out before you do the boom. This guy's coming down to 0. This right here is at negative 1.645. This is a positive 1.645. That's cool. So now the question is, once that is set up, we'll just have to figure out, is it in the rejection region, yes or no? All right, all yours then. Calculate. The Z value here. All right, what we have to do is we have to calculate our own P value, right? Our P hat. So let's do that here. Let's see if that makes sense. Our P hat is X was the number of people that said yes in our survey was 1,161. Divide by N, which is 2,202. And so our P hat value is 0.527. Are we good there? All right, on your calculator, see if you guys can get that number right there. If not, please ask. I'll come by as well. So hopefully you guys get a 1.60. That's what I'm looking for. All right, try it yourself here. Please do. Let me pause real quick here. I should do it for the video, huh? So let me do it for the video real quickly here. All right, those of you that are working on this here, I got the, yeah, let me just show it to you here on the video here. So if you want to if you want to do it all in one single step, let's say like, look, Mr. NG, I want to do it one single step. Okay, fine. You have to put extra parentheses around the top. So it's this one right here, then it's 0.527 minus 0.51, because that's going to keep everything in the denominator. We good? Then we divide by the square root of 0.51 times 0.49 divided by 2202. We don't need the extra parenthesis for the 2202 because it's just a single divider. If we had multiple things in there, then we have to keep them all together. So with that said, voila, we're good. If you can do it separately, I would do the top 0.527 minus 0.51. Notice I'm using an extra zero in one of them, not an extra zero in the other. That's okay. Okay, if you get this answer, you did them separately, just click your divide button. Because what happens is this number here actually gets put into the next entry already. So then you say, oh, divide by the square root of, and then we do the same thing here, 0.51 times 0.49 divided by 2202. And voila, we good? Okay, all the different things we can do in the calculator. There it is. Let's go for it here. So here's what we've got. Rejection region starts at 1.645. We are at 1.60. So we failed to reject the null hypothesis. So there's not enough evidence at the 10% level to reject the claim that 51% of US adults believe that antibiotics are effective against viruses. Okay, boom. And that wraps it up for 7.4, and we're jamming to 7.5. Okay, guys, last section. This is crazy. This is it. Down. So hypothesis testing, no longer for the average. We don't look at the average anymore. Hypothesis testing for, we're no longer looking for the proportions, right? It's not a percentage of things happening, right? So not looking at the mean, we're looking at the standard deviation of the variance. So how much spread you have, that's kind of what we're looking at. How much spread you have for this. So it's variance and standard deviation. That's what we're checking for. Okay, let's begin. All right, so here's what it is. So intro was done. The means were right over here. We're looking at the means, proportions, and now we're going to take a look at a whole new entity called variance standard deviation. If you guys look back at 6.5, chapter 6.5, you'll notice we did the same thing for confidence intervals. It was variance standard deviation. So we used something called a chi-squared test, exactly the same thing we're going to use now. So don't write this down. Let's think with me here. Same exact process. We're going to figure out what alpha means. We're going to take degrees of freedom. We're going to try to figure out if it's a right tail test, a left tail test, or a two tail test, right? Boom, boom, boom. That's all we need out of it. And then we're going to test it. So what does it look like on a graph? It looks like this. So notice these guys are no longer symmetric, right? The chi-squared test looks at these values like this. And so a right tail test looks like this. Alpha is on this side, left tail test. And then if you're looking at both, we cut alpha in half to get the two tail test. So exact same process, exact same things to go with. So let's practice just getting the values just like we did last time here. So let's practice getting the values. Can you find for me the critical values for chi-squared? If we have n is equal to 26, alpha is equal to a 0.10. Okay, so now we'll go take a look at our textbook. And I'm going to go jump to a little different section here. All right, on page A19, I'm gonna have to leave that on here. Let's see, A19. It's in the appendix. It's not at the back cover. It's not the back cover that we had before. This is actually coming into the textbook already, into the textbook a little bit. And we're looking at Appendix B. Let's see, Appendix A starts off. Let me see where Appendix A starts off. It starts off chapter 10 or chapter 10 finishes on page 581. That's the last page of chapter 10. Then once you flip past that, you get Appendix A. So you flip through Appendix A, just a few pages. Appendix B starts on A7, and then just flip a little bit more. 12 more pages past that, and you get to something called the chi-square distribution right here. It's called Table 6. Table 6 chi-square distribution. And so we go with it here. So boom, look at this guy, degrees of freedom, very similar to the t-test here. So degrees of freedom would be 25. Go down to 25. It is a one-tailed test, it's a left-tailed test. So alpha stays at 0.10. And hopefully you found this little guy called 34.382. So again, take a look at that. Good, good. All right, thumbs up if you got it. Boom, boom, boom. Okay. So that is a left tail test. Okay, another one here. All yours for this one. N is equal to 11. Find me a left tail test for 0.01. Okay, yeah, that's what I thought here. So real quick here, this one should have been a right tail test. That is wrong. Let me just check. So check real quick here before, just to make sure. Okay, yeah. That's done wrong. So right tail, you could tell because the tail is to the right on this side. So that should be a right tail test, not a left tail test. Okay, this is a left tail test now. Left tail test, N is equal to 11, alpha is 0.01, so 99% level. Degrees of freedom would be then 10. And what are we looking for now? Well, our left tail test, because the chi distribution starts from the right this time, not from the left. So when we look at this here, we're going to say 1 minus alpha is 0.99, and that's the one that we want to use. So the chi-square test, you know how the cumulative area goes from the left for the z-score? And the t-score from the chi-square test, it goes from the right this time. So if you do that, you got to look at the 0.99 value. And the 0.99 value tells you you got a 2.558. So all yours trying to find that one. Make sure you guys got that one. Okay. And again, thumbs up real quick here if you guys got it. Okay. I'm going to give you guys the table. Yeah, I got to give you guys the table. That one and the T. I'll have to print you guys out table. Okay, got that. And then let's jam with, and of course, a two-tail test. Give me the left side and the right side. For n is equal to 9, alpha level of 95% or 0.05. Okay, what do we do here? We've got to think about. So that was pretty easy because on the t distribution, it tells you if you had a one tail or a two tail, huh? This is no fun. It doesn't tell you the one or two tail. So we have to calculate now stuff. So degrees of freedom, what do you guys say? 8, right? Degrees of freedom is 8. So DF is 8. And now the fun begins. Because it's a two tail, alpha is 0.05. So let me kind of just draw this out as we kind of just have an understanding of it here. So it goes like this. Right? So that means half of it should be over here on this side. So what's really saying is I want 95% of the data here. So 5% goes to the corners. So that means half of that is going to go here. 0.025. And 0.025 is going to go here. All right, so that means we're going to look for this guy right here. We good? We're going to look for the right tail test because who cares if it's right or left? We're going to get the right tail test with n is equal to 8. Well, then we have to do this one too, huh? Okay. Okay, so if this was all the way colored in, you guys talk to me. If this was all the way colored in, what would this be right here? What would be the left side be? It's like, let's see, what's 1 minus 0.025? Yeah, this is 0.975, right? Okay, so looking for those values. So we're looking for a table. So let's go down the table here. We go down the table to 8 over here, running across. And as you run across, we're looking for 0.975 to do our left side. And what'd you guys get there? .108, perfect. Okay, cool. And then we're gonna, so the right side, we're gonna keep on going across the top row here to a 0.025. Look down for 8 again. What do we have there? Something about 17. Perfect, okay. Again, thumbs up if you got to both of those guys. Boom, boom, boom. Not as many thumbs up this time here. Giselle, you doing okay? Did you? Say again? We are on table 6, And so we're gonna go down to the 8th row, or number 8 for degrees of freedom. And because it's 95% here, we had to split the alpha into 2 different pieces. So we're looking for 0.025 as our right side. But I just started looking at the left side first. So then if this was all colored in right here, then we'd be looking for 0.975 for the left. So it's 1, 2, 3. It's the third column in. Third column in, going down all the way to DF equals 8, 2.180. Are we good there? Scrolling off to the right so that you're under 0.025 now. How about a 17.535? Cool. Okay, that's it, guys. That's kind of, we're just using a different chart. So now let's begin. Let's get our formula going, and then we'll go from there. Formula is, there it is, the chi-square test. Don't need to write all this down, but the chi-square test is for variance and standard deviation. That's what it's made for. The formula right over here. So chi, make it like a capital X, but then kind of make it slanted a little bit here. Kind of slant the X. It's not really an X. It's not a capital X either. It's a slanted Greek letter. So chi squared is your standardized test statistic. N minus 1 is what we have. Whatever we get for the standard deviation squared divided by population standard deviation squared, or variance, I guess. So really what we're doing is we're looking at degrees of freedom as our multiplier. That's what we have. So the DF is our multiplier. Okay, just write that formula down so you have it. Okay, also don't forget for the test, right? It's one sheet of paper. All the formulas you think you have or need, write them down for the test. So we got 1, 2, 3. Take three examples here as we go. Yes, we had something similar in chapter 4 and chapter 6, 6.5. We did the chi-square test for confidence. Cool. All right, I'm going to go for it here. Just as long as you have that, this little guy right here, that's the form that we need. We'll fill in the rest of it if we need to. Okay, let's go. 3 examples here. Let's jam. Here it is. A dairy processing company claims the variance of the amount of fat in the whole milk processing by the company is no more than 0.25. So you suspect this is wrong and find that a random sample of 41 milk containers has a variance of 0.27. So at the 5% conference, is there enough evidence to reject the company's claim? So think about it, one-side or two-sided tails. That's the first thing to sort of come through our mind. All right, so let's go with it. Can you guys list for me H naught, the null hypothesis, and the alternative hypothesis? Can you guys do that? So list it down first, and let's see what we got here. And again, the process is still exactly the same that we had before. All right, let's see if this makes sense. Because the sample is random, population is normally distributed. Yes, that's cool. We can use the chi-squared test. The claim, here's our claim. The variance is no more than 0.25. No more than 0.25. So it could be 0.25, right? Or less. So null hypothesis. And remember, variance is the square term of a standard deviation, right? So it's S squared is what we're using now. Less than or equal to 0.25. That's our claim. alternative hypothesis says that the variance is going to be greater than 0.25. That's it. And this, as we look at it here, we assume that this is true. Null hypothesis is true, so everything is less than 0.25. That looks to me like a right tail test. Is that right? Rejection region would be off to the right. It would be like this right here. So if we assume this to be true, that everything is less than 0.25, if 0.25 is here, right? That means rejection region is going to be on this side. That's a right tail test for me. That's perfect. Okay, we got that. So let's plug it into our little formula in our table, table 6. Can you guys give me the critical value? What's the critical value here? Degrees of freedom is 40 at this point. And the alpha level is set to 0.05. Okay, all yours to tell me what that is. Something like 55 or something like that, is that right? That area, oh, sorry, real quick here. So I got this one right here, 55.758. Okay, thumbs up if you found it on your chart. Boom, boom, boom. Okay, those that have a book with you. Cool. Okay, then we're gonna try this on the calculator now. Then we're actually going to check if it hits the rejection region or not. So chi-squared would be degrees of freedom, which is 40. And what we found in our test is that we found a variance of, let's go back over here, right there. This is what we found, 0.27. So we're going to use that little figure right there now. 0.27. Multiply the top, divide by 0.25. So all yours. This one you could probably just do 40. So 40 times 0.27 divided by 0.25. Okay. And then thumbs up when you guys get 43.2 on your calculator. And then after that, if you got that, can you draw it out? Just like we've been drawing these guys. All right, quick thumbs up if you got 43.2. Boom, boom, boom. Okay. All right, and then can you draw it out? Draw out what it means. And the graph should be not like a symmetric anymore. You could just do it symmetric if you like. Chi-squared region kind of, it's a little bit off. It's not as symmetric, but if you just want to do a symmetry, that's fine. The average is 1 second, let me see this real quick here. Yeah, I guess so. Let's see. We can just put a graph out. And it's just chi-squared. It's the values for chi-squared. That's where we're at. So even though it's not fully, if you guys want to do the graph, kind of looks like on table 6, the graph kind of like this right here. That's fine too. Just kind of, it's slightly right-tailed a little bit. Okay. Well, let's go with it here. So we have the border for our critical point is 55.758. We hit a 43.2. We cannot get to the critical value. So we failed to reject the null hypothesis. We're good. We didn't get into the rejection region here. And so because our claim is the null hypothesis, therefore there's not enough information at the 5% level to reject the company's claim. Okay, are we good there? We're good? Guys, still the same process, just goes over again. It seems like we are dreary and dull sometimes because it's just the same process. Okay, let's go with it. 2 more. A company claims, here it is at this, standard deviation. This is a little different. Company claims that the standard deviation of the length of time it takes an incoming call to be transferred to the correct office is less than 1.4 minutes. Oh, that's cool. Yeah, if you're looking for a call center, it's exactly what and then raise your hand if you've been on the phone for like at least half an hour and then never got through where you needed to get through. Okay, yeah, absolutely. So a random sample of 25 incoming calls has a standard deviation of 1.1 minutes. At alpha is 0.10. Is there enough evidence to support the company's claim? Okay, let's go with it. 2 more to go. So first things first, this is in regards to standard deviation now, right? So let's see, and it is the it is standard deviation. Okay, yeah, the standard deviation, the lengths of times it takes. So it's not so much as it takes less than 1.4 minutes, right? It's just the spread of time. So the call center could take 20 minutes to get through, right? But it just means that it's going to be in a very narrow span of time. Not like one is like 5 minutes, the other one's 35 minutes. Okay, let's go with it there. So here it is. Since this is less than 1.4 minutes, the less than symbol goes with the alternative hypothesis, and that's our claim. That means the null hypothesis would have to be the exact opposite. Null hypothesis standard deviation is greater than or equal to 1.4 minutes. Okay, 2-tailed or 1-tailed? It's 1-tailed, right? It's going to go a certain direction. So if we assume the null hypothesis is true, we want to get above 1.1, greater than 1.4 minutes. It's a 2-tailed test from the left side. Is that right? If you're to graph it here, let me graph it real quickly here. It'd be something looks like this right here, right? It goes like this. If that's true, the rejection region would have to be somewhere over here, right? The rejection region would have to be on the left side of it. Okay, that's cool. So let's see, we need a few things here. The DF value is equal to let's see, 24, 25, right? There's 25, yeah, in random calls. So 25 minus 1. I got 24 for my degrees of freedom value. It's a 1-tailed test. And what's the alpha level? I don't have it in front of me here. 0.10, perfect. Okay, from the right side, sorry. And so from the right side, it would be 0.10. So therefore, from the right side, this guy will be 0.90. That's what we're looking for. Okay, we're good there for the 0.90. Okay, so find me this value here. So alpha level 0.90. Degrees of freedom is 24. Awesome. Okay. 15.659. Boom. Thumbs up if you guys got that. All right. I like that. Okay. Cool. Those that don't have a book, I'm so sorry. So you're going to try it at home here. Okay. So now let's calculate our chi-squared value here. Ours would be what, 24? Now this time, notice you have to square it, right? Because that is a standard deviation now. The standard deviation for us was 1.1 minute. We didn't square it last time because that was already variance already to begin with here. So now this is 24 times 1.1 squared divided by 1.4 squared. Okay, and try it. See if you guys get a 14.816 and a thumbs up when you do, or else I'll just call for it in just a bit here. All right, how many got a 14.816 on the calculator? Cool, okay. All right, and then let's draw it out. Let's see, it should look like this right here, right? So the critical value is 15.659. Our chi-squared value that we calculate is 14.816. Hey, we actually are in the rejection region. Kind of funny because it's lower, right? We expect that to be higher or lower, but yes, it is in the rejection region. Perfect. So we reject the null hypothesis. So what does that mean? It means that there is enough evidence at the 10% level to support the claim. So we reject the null hypothesis. The claim was let's look at the claim real quickly here. Which one's the claim? Okay, yeah, the claim was the alternative hypothesis. Yes, so there is evidence to support the alternative hypothesis. Okay, one more, last one. Here we go. A sporting goods manufacturer claims that the variance of the strength in a certain fishing line is 15.9 pounds per square inch or whatever it is. A random sample of 15 fishing pole spools has a variance of 21.8 at an alpha significance 0.015. Is there enough evidence to reject the manufacturer's claim? Assume the population is normally distributed. Here it is. So technically, if you guys think about it, we did a right tail test. We did a left tail test. And guess what? This has to be a two tail test. Absolutely. Okay. Last one for it. Let's go with it. Can you guys give me the HO and HA? Give me the null hypothesis. Let's finish strong with this one here. So put down HO, put down the null hypothesis, put down HA, the alternative hypothesis, if you can. So what's the claim by the manufacturer? That the strength in a certain finishing line is 15.9. That's their strength right there. So that the variance of the strength is 15.9. Okay, so variance would be the squared unit of that. So it's sigma squared each time. And I have something that looks like this. Let's see if this makes sense here. So H naught is sigma squared, which is variance equals to 15.9, and that's our claim. The alternative hypothesis is the fact that variance is not 15.9. That's what we got here. Degrees of freedom is 14. Alpha level of 0.05. We have a two-tail test on our hands. Talk to me. What's your chi-squared value? This time we actually need both values, right? We need the left and the right, like we practiced before. So if you were to graph this, right, it goes like this. So 95% happens right here. That means 0.025 is here, 0.025 is here. So the right is taken care of. We can do that by the right. So now the question is, to get this one, we need 1 minus 0.025, which is 0.9725, because we did that already when we were practicing this stuff. Okay, I need a chi-squared left, and then I need a chi-squared right. You guys talk to me what those are. Sorry, writing it over because it was not nice. Okay, go for it. Chi-squared left or chi-squared right, whichever one. 5.629, okay. Boom, okay. Chi-squared right. Six 6.119, perfecto. Okay, there's my limits. If I want to, I can start doing my graph if I like. So then can you calculate the chi-squared value that we got? All right, something about 19-ish. Go with that here. So let's see, this should be 14 times 21.8. Divide that by 15.9. And we get ourselves 19.192. If you make a graphic of it, are we in the rejection region or not? That's the question. So make a graph of it. We've got to be at 26 on the right. We're only at 19. And so we're not in there. We failed to reject the null hypothesis and then their claim. Let's see our claim. What's our claim? Our claim is the null hypothesis. So there's not enough evidence at the 5-degree level to reject the claim that the variance of the strings of the fishing line is 1.5. So we keep it still. All right, that is the end of chapter 5. Good job hanging in there. I hope you guys just noticed it was pretty much the same exact stuff, same, just which formula do you need to use to which test.